Calorie consumption problem. The number of calories an animal must consume per day increases with its body mass. However, the number of calories per kilogram of body mass decreases with mass because larger animals have a lower surface to volume ratio. Right? So, this was actually taken, the following data is taken from page 130 of Studies in Mathematics, volume 20, published by Yale University Press in 1972. And this is the data about these animals, okay? So, if your animal is a guinea pig, then its mass, they measured it on the absolute average. So, the mass of a guinea pig, the average is 0.7 kilograms. And the number of calories per kilogram of body mass of this guinea pig is 223. Okay, so take note of that, 223 calories per kilogram. So a guinea pig of 0.7 kilograms has what they call this, it consumes a notably, huge amount of calorie per kilogram. And as we go further, we go with the heavier animal, like consider the rabbit, okay? So the rabbit here, on the average, has a mass of 2 kilograms, and it consumes around 58 calories per kilogram. Okay? While the human, on the average, is 70 kilograms. Well, I am about 60 kilograms. So an average human with 70 kilograms consumes 33 calories per kilogram. Okay? While the horse, which is 600 kilograms by mass, then it consumes 22 calories per kilogram. And while the elephant, which is, let's say, it weighs 4,000 kilograms, then the number of calories per kilogram that it consumes is 13. So notice that an increase in the mass is leading to a decrease in the consumption of calories per kilogram. And this is what is proven or studied by the Yale University, the Max Bell, okay, and on page 130 of Studies in Mathematics, volume 20, which is published by Yale University Press. Okay, so letter A, make a scatter plot of the data. Explain why the scatter plot does not tell you very much about the relationship between the variables. Then transform the data by taking the logarithm of the mass and the logarithm of the calorie consumption per kilogram. Run a linear regression on the transformed data and plot it on the same screen as a scatter plot of log calorie per kilogram versus log of mass. Okay. Okay, so let's take the log of mass in kilograms and the log of calories per kilogram. So let's start with the guinea pig. The guinea pig has a mass of 0.7, so log of 0.7, that will give you 0.1549 continuous, and log of 2, so log of 2 will give you 0.3010. Okay, log of 70, that would give us 1.8451 or 0. Okay, sorry about that. Okay, 50. Okay, log of 600, this will give us 2.7781. And of course, the log of the mass of an average elephant, which is 4,000. So log of 4,000 will give us 3.6020. Okay? Now let's go to the log of the calorie per kilogram. So let's start with consumption of the guinea pig, which is log of 2 to 3, and that is, okay, let me use this, 2.3483 log of 58, which is that of a rabbit, okay, which is 1.7634, and then the human, so log of 33, this is the consumption, 1.5185, and then next is the horse, so this is log of 22, and this will give us 1.3424. Okay, and lastly we have the log of the elephant, so log of 13, which is 1.1139. Okay, so we got the logarithm of the mass and the logarithm of the calorie consumption per kilogram. So based on your grapher, if you have an input of this data, this log of mass, log of calorie per kilogram on your calculator, then the regression will give you, it will give us something of a value, and that value is equal to, okay, let me prepare the data. The running the regression will give us log y is equal to, of course, using our data here. So our data is this columns now. So we have log of y hat actually running the regression. Okay, that's negative 0.2774 log x plus 2.0817. And what is the coefficient of correlation? What is our R? Our R here is, or let's say R squared, the coefficient of determination first, so that's 0.8773. Okay, running a regression analysis on this. And if we are to plot the log of the mass versus the log of the calorie per kilogram, where our x is the mass and the calorie per kilogram is the the x is log of mass. This will be our x now, and this is our y. So let's call it like log y and log of x. Okay, so if we are going to plot to draw a scatter plot of this graph of the log mass, log calorie over a kilogram, and that's what you call the transform data, okay, then we are going to get this. Okay, so we are plotting this data now. We have 1, 2, 3, 4, 5. We have 5 data here. 1, 2, 3, 4, 5. Okay, so letter B, by transforming the equation, in part A, show that the calorie consumption is a power function of mass. By running power regression on the original data, show that you get the same power function. Okay, now let's do that. So how are we going to do that? Of course, we have the transform data, right? And followed by the transform logarithmic regression. So we have log y, or log y hat, is equal to a log x plus b. Okay, and right, am I correct? Yes, it is actually on the same format, right? Now running the or transforming this to a common log, we will have y hat is equal to 10 raised to a log x plus b. Am I correct? Okay, now I could actually expand this and I will get 10 raised to a log x times 10 raised to b, right? And this is actually equal to 10 log x, right, times a, right, and times 10 raised to b. Okay, so let's say we have this constant 10b. Okay, let's rearrange the terms. So 10b first times 10 okay, 10 log x times a. So that would be, if we're going to combine this thing here, okay, that will give us bx raised to a. Am I correct? Okay. And this is actually equal to 10 raised to 2.0817 x raised to negative 0.2774, or in other words, this is equal to 120.7251 x raised to negative 0.2774, okay, which is pretty much the same equation that we found for power regression, with r squared is equal to 0.8773 as in part A. So remember, our part A is this. So it's the same equation, okay, that we found here, right? So by transforming the data, the value wouldn't change. It's a power function. Now when you get the log of those terms, then you get the power function, and still when you get the logarithmic regression, they are similar. Okay, so nothing changes actually. So letter C, the smallest mammal is the shrew. Predict the calorie consumption per kilogram for a 2-gram shrew. They need to eat so much compared to body mass is probably why the shrews are so mean. Because remember, the relationship between the mass of a certain animal as compared to its consumption is pretty, what do you call this? I think this is like a variation, right? Like the mass, if the mass increases, the consumption decreases, right? So the reverse is also true. If the mass decreases, the consumption increases. So in here we have a 2 grams through, meaning that following the power regression that we actually took from this computation, then y hat is equal to, we always begin with that, okay? Y hat is equal to, what did we get? 120.7251. 120.7251 x negative 0.2774. Now I'm going to get the y hat, or the consumption of the shrew, which is the smallest mammal ever living. So we have y hat of, what is 2 gram? because our animals are in kilograms, so we need to convert it to kilogram also. So 2 divided by 1000, that's equal to 0.002. So that's equal to 120.7251 x negative 0. And what is our x? Our x is 0.002 raised to negative 0.2774. Okay, and the answer here is, let's do that. Computing for the consumption calorie per kilogram of the straw will give us 120.7251 times 0.002 raised to negative 0.2774, and we've got an amazing 676.84 calorie per kilogram. Okay, which is approximately 677 calorie per kilogram. Wow. Okay. In letter D, in the reference article, Bell reports that a 150 kilogram whale consumes about 1.7 calorie per kilogram. What does the power function predict for the calories per kilogram if you extrapolate it to the mass of a whale? And by what percentage does the answer differ from the given 1.7 calorie per kilogram? Think of a reason why the predicted value is so far from the reported value. Okay, let's do that using the power function taken from the regression uh, analysis. Okay, so y hat of 150,000 kilograms using this power function, of course. So we have 120.7251, then we have 150,000 raised to negative 0.2774. Okay, let's change this, negative 0.2774, so you could see. Okay, so we have 120.7251 times 150,000. Wow, a whale is so huge, right? So negative 0.2774. And look at this. The answer is actually 4.425 calorie per kilogram. It's not 1.7 calorie per kilogram as reported. Why is that so? This is around 160% of the total value, or the reported value, because this is 4.425 divided by what is the reported 1.7 times 100%, that is equal to divided by 1.7. We have 260% of a difference. So look at this gap. The difference is 260% of the actual value. Okay, because we are extrapolating. Note that extrapolation is this cannot be trusted. Extrapolation, it couldn't predict the future. Okay, because we are extrapolating beyond or far of the given x. So if we're extrapolating to beyond the range of the x value, then we could not always predict the what do you call this? We could not always predict for the consumption of calories per kilogram because we are look at our what do you call this? Look at our range for the mass. It's 0.7 up to 4,000. and we are extrapolating for 150,000 kilogram whale. So it is out of the range. Our greatest is 4,000 kilogram, right? So we couldn't always predict a good, what do you call this? We couldn't always have an accurate prediction for the calories per kilogram of the whale as reported. Okay? So that's it for this problem. It's about the calorie consumption of animals from the shrew to the guinea pig to the rabbit to the elephant, and elephant is our limit here. And when we go beyond that, such as the whale, which is far, far beyond the elephant in terms of the mass, then we couldn't get a good prediction. Okay? So once again, thank you for watching and have a nice day.